And, and I always say, okay, and I'm aware of it every once in a while, that just that's my attention. So we have a bunch of different questions here in this next example where it's asking the questions to actually figure out answers, to get your answers. But the first step of it is to decide whether this is something that's modeled in linear or exponential change. Is it linear increase, linear decrease? Is it exponential growth or exponential decay? So let's just go through them one at a time. So the first one is number of students at Wilson High School has increased by 50 each of the past 4 years. If the student population was 754 years ago, what is it today? So I don't want to answer the entire question, but what's your impression on this one? Should this be linear or exponential change? Wait, not good this time. I have my little sheet here. Got it. Here we are. What do you say for this one? Does this sound like a scenario linear or exponential? Linear growth. Linear, it's going to be linear growth. It's saying that it's increasing by a constant amount, 50 for each time. 50. So it's linear growth. We'll come back to answering that because it's going to ask us all of these different questions first individually. So B, the price of milk has been rising 3% per year. The price of a gallon of milk was $4 a year ago. What's it now? So is this one linear or exponential growth? It is growth. Yeah.
Exponential.
So the exponential because it's giving you the growth in relative amount. So whatever the price is.
Thank you.
So we'll come back to that one also, do the arithmetic. Okay, next one. Next one says tax law allows you to appreciate the value of your equipment by $200 a year. If you purchased the equipment 2 years ago for $1,000, what's the depreciated value today? So what would you say on this one? Is this a linear change or exponential change? What would you say?
Is it still linear?
Yeah, it's going to be linear. That's right. It's going to be linear because it's a constant amount that's changing for each time. So that's a linear change. But come back to doing the arithmetic, but the first step is just identify. D, the memory capacity of state-of-the-art computer storage devices is doubling approximately every 2 years. If the company's top-of-the-line drive was 60 terabytes, they level are 60. So what type of change is happening here? Is it a linear change or an exponential change? It's exponential. That's right. It's exponential because it's saying it's doubling. It's telling you that it's growing by 100%. It's being multiplied by a factor of 2 for every time period. Every 2 years, it's being multiplied by a factor of 2. So that's a relative change. Because of course, if it's larger to begin with, then multiplied by 2 is a different change than if it's smaller. Multiplying the total amount of change. And the fifth example, this is the last of the little section here. The price of high definition TV sets has been falling by about 25% a year. The price of $1,000 a day, what do you expect it to be in 2 years? So again, is this an exponential or linear change? Yeah.
Exponential.
This is exponential, exactly, because it's giving you a relative change. Whatever the value is at the time, it's changing by a percentage of that value. Okay. So, and this one, since obviously the quantities are going down, prices falling, we would call that exponential decay. So decay and growth, it's nothing fancy with plug in 3 for x, this is 3 years. And that gives you the value. So 1,000 minus 200 times 3. So that gives you 400. And we can check what they go over here. They look at the value increase, the same absolute amount of years, because it's linear decay. I like that number, linear decay. It makes sense that it's always the only place in the world that anybody says linear decay. It's a linear change, it's a linear function. In 3 years, the value increases by 3 times $260. So the value increases to $400 from $1,000. Let's go back to Big D then. The memory capacity of state-of-the-art computer storage devices has doubled approximately over 2 years. We said that means it's going to be exponential growth. The company's top-of-the-line drive holds 16 terabytes today, what will it hold in 6 years? Okay, how can we go about figuring this one? It's a good challenge. One of the weird things with this one is that the time period that we're talking about are chunks of 2 years. So if we're talking about in total a 6-year time period, we're talking about chunks of 2 years. How many chunks are there? There would be 3, right? 3 times that something has. So 3 times the memory capacity is going to double. So that means it's going to go up by a factor of what? It's going to double once, it's going to be 2 times bigger, it's going to double twice, it's going to be how much bigger? 4 times bigger, right? And it's going to double again, that's going to make it 8 times bigger. Multiply by 2 3 times. That's what it's saying, you're doubling 3 times. So it's going to go up by a factor of 8, and so 16 terabytes, 16 times 8 is 128, right? 128. Right, 16 times 2, 32 times 2 again, that's 64 times 2, 100. So it's going to be 128 terabytes. So let's see how it's described here. Doubling is the same as a 100% increase, so the 2-year doubling time represents exponential growth. We're going to determine that. Well, if it's doubling every 2 years, the capacity to double 3 times in 6 years, from 16 to 32, 32 to 64, 64 to 120. Okay, so yeah, these are very nice explanations. I really like it because you're actually getting straight to the linear model. And that's actually very nice because if you're able to do that abstraction, you really know how to handle this stuff and do the arithmetic for figuring out problems when they're complicated. But we mostly don't need that. We mostly don't need that. What we do need is to have a sense of how quantities are changing with linear growth relative to exponential growth. We need to have a sense of when we have linear growth versus exponential. And that's actually what this exercise here is all about. We started going through saying, given this description of our scenario, what's happening? Is it linear growth? Is it exponential growth? Or linear decay? Yes, exponential decay. And then try to just reason and figure out the quantity, because we're able to do it even without coming up with a function. And that's valuable. That's the most important thing for this section. Okay, we still have E to do. So E says the price of high definition TV sets has been falling by about 25% per year. The price is $1,000 a day. What can you expect to be in 2 years? Okay, well, this one we said was exponential decay for this one because it's going down. Price. And so, well, if the price is $1,000 a day and it's dropping by 25% per year, what will it be in 1 year? What will the price be? It'll be $750, right? It's going to drop by 25%. That's the same as multiplying by 0.75 or subtracting 25% of the $1,000. It's going to be 750. And then we need to do that again. Well, I can bring up the calculator. Let's see. So if we have $1,000, we want to, if it drops by 25%, then it retains 75% of its value, right? So 0.75 to have a single bacteria in a bottle of 11 in it. Each minute, this thing is dividing double the population of bacteria. So after 1 minute, it divides into 2 bacteria. And another minute later, both of those two divide and have 4 bacteria. And then 3, it divides again, so each of those 4 divide into 2. Now you have 8 bacteria. And it says, at noon, the bottle is full. It's completely full. Okay. Completely full of bacteria at noon, which that would mean that it has 2 to the, yeah, that's 60. So it's just 2 to the 60 bacteria. It's a huge number, 2 to the 60 bacteria. Now, it says they're very concerned about the bacteria. It says that bacteria fill the bottles, the entire bacteria bottle is doomed because the next time they double, I guess they implode or something. I don't know, the entire population is doomed. But interesting question though. Interesting question. If the bottle is full at noon, at what time is it half full? So at what? So 12 o'clock it's full, at 11 it just had 1 bacteria. So at what time is it half full? What do you think? Okay. Last minute. That's right, it's 11:59. It's 1 minute beforehand. The population is doubling every minute. So if it fills the bottle at noon, 1 minute before, it had to have been half that size. Because in that last minute it doubled. Right? So that's an interesting question. I think that, well, I got a question here. Disaster occurred, bacterial disaster. Occurred because the bottle's completely full. At noon, the room was half full. Because it took 1 hour to fill the bottle, and we guessed it was half full after half an hour. That would be linear growth. But because they double every minute, it must have doubled the last minute. And so it was half full 1 minute before. Half full 1 minute before. Okay, so that's the character of exponential growth. It's completely different than the character of linear growth. Most of your growth is occurring at the very end. Most of it is right at the end. So we have a bunch of doubling times for something that's exponentially growing. The last time period, it grew as much as all of history before it. So that's how exponential growth is. Everything is happening, almost everything is happening at the end. Okay, and that's like what? That's like investments. That's like investments. You have compound interest. You have doubling times. Your last doubling time, half of the entire growth of your balance through all of the history of your investment is that last doubling time. So if you're lucky and you get good behavior in the market, you double, let's say, 12 years, doubling time, something like that. And you work until you're 65, your value at 53 in your account is half what it would be at 65. But there's the last 12 years it doubled. But from 53 to 20, whatever, that rest of it was all accumulating the same amount that you ended up accumulating right there in the last 12 years. That's how exponential stuff works. So basically life sucks until you get old enough to not be able to enjoy it anymore. Right? On my shoulder. I have to go around carrying my arm and the leg doesn't work out. You see me up here, I'm doing this stuff all the time. Nervous back here. Oh, well, I have kids. They can be wasteful and lose all the time. Alright, so number of bottles. How many bottles of bacteria fill in a second alcohol?
Oh.
Ridiculous question. How many do you think? It took them an hour to fill up this bottle. How long do you think it would take them to fill, or how many bottles do you think it would end up filling up at the end of the second hour? Yeah. A lot more than 4. Remember, it doubles every minute. So at 12:01, they would fill 2 bottles. At 12:02, they would fill 4 bottles. At 12:03, they'd fill 8 bottles. At the can still fit that on Earth. That's not so big of a big escape Earth. I remember, I think that Earth is something maybe 6 to 8 tons, metric tons maybe. And now I'm curious. Mass of Earth. Very big. So let's see, that was, that's septum. Yeah, that's septum kilograms. So take away 1,000. Yeah, it's about 6 trillion tons.
Dang.
Tons like metric tons, right? 1,000. Yeah, that's great. So they would still fit on Earth, but it wouldn't take very long for the number of bacteria to be larger than the number of subatomic particles in the universe. So, I mean, that's the nature of exponential growth. Exponential growth doesn't really exist. It's not really purely something that exists. If you take a petri dish and put bacteria in them, when they start growing, it's going to appear like exponential growth. But what it actually is not. It's something else called logistic growth. It's logistic growth. It grows up very similar to an exponential function. Once you start getting competition for the limited resources you have, the growth no longer is increasing. It's at its maximum amount. Then the growth still happens. The population is still going up, but it tapers off in its growth, and then it approaches a limit. And different things can happen in reality. It could be that the resources can't be replenished, so then you have sort of a really slow replenishment. Then you may have a die-off, so you may have some sort of cyclic phenomenon. Or it could be just like pure logistic growth, where there's a finite amount of resources, but they're always maintained, and then you just approach this thing. Oh, there are a lot of things that work just like that you might be interested in. I'm ignorant, so I'm going to start. Rumors. The spread of rumors follows logistic growth. And logistic growth is one of these things, it's like the population graph we saw at the beginning where the exponential growth is like this. It starts off like that, but then it reaches its steepest point, and then it tapers off on the spot. And the interesting thing about that curve is that the place where it stops increasing faster, right? It stops curving up, it starts curving out. That's half the height of where it ultimately is. That's just the nature of it. And rumors spread that way. Rumors spread exactly that way. Ultimately, you're going to have, if the rumors spread in the classroom, so I went through something to do, and I say some super sordid secret professors in the math department to you, you whisper it to everybody else around here. I mean, slowly over time, it would fill up the room, basically, everybody who's willing to have something to whisper to would know, and the others would be like, I don't want you to whisper things to me. That's the nature of rumors, but I could actually put a plot of how many people know in time, and at some point, just based off of the shape of the curve, I'll actually know ultimately how many people are going to. You can actually predict how many people are going to know people altogether. Some people are just not interested or not doing it. They just don't want to do it. And you can figure that out. And this is actually extremely important for things that you might actually care about. An example I always love to give for this whenever we talk about properties in that calculus. I teach that function in calculus. So market share. Back in the 90s, all of the shopping malls had Pepsi Blue. It's not Crystal Pepsi, you've probably heard about. Pepsi Blue was a failed venture that just existed for a few months. Pepsi Blue, I believe it was just Pepsi that had blue fruit coloring. That was the idea. They're just trying something else. Crystal Pepsi failed also, so why not just do blue Pepsi? But they called it Pepsi Blue, and they gave them out for free. You could just go and get a 6-pack of their handed out at shopping malls for people to try. And the idea is get knowledge about this product out there, and then test and see how many people are actually interested. Do surveys, see how many people are interested in buying this thing. And so as people that sum off at some point, your sum is one less than the next number you're going to add. So 1 plus 2 is 3, and that's one less than the next number I'm going to add 4. 1 plus 2 plus 4, that's 7. That's one less than the next number I'm going to add 8. This is just making a comment about that. That the last number that you add is about the same as all the previous numbers you added to that. That is a characteristic of exponential. That's a characteristic. Exponential growth did not move that way because the universe is finite, at least the observers are probably interactive, which is even smaller than the observable part. That's fine. We just can't get beyond a certain distance. So you can't have exponential growth. And that's it. Yeah, actually, I think that's about all there is to say. We're not going to dwell on the actual format of this function, but we're going to look at the exponential functions. We're not going to do that. The purpose of putting this section in here is just to talk about the character of linear growth versus exponential growth, and have it be sort of a bookend to the financial discussion we had in chapter 4. Because you fully have the potential by your choices to get exponential growth with your investments. You do that, absolutely have that potential. It's hard to get big amounts, it is. But it is not hard to do the exponential growth. And you saw that the time period matters for this. So like the bacteria model, put one bacteria in, okay, after 6 minutes, it's going to be, 64 bacteria. That's not huge bacteria time, right? But by the end, you can quickly fill up the bottle. If you had another hour, then you have enough to basically fill up the surface of the earth, bottles of this bacteria. So the number is the same thing for money. So you have your investments, the more time you have, the better it is for your growth. So the extent to which you can start early and start putting that stuff and bear fruit, that's really going to make a tremendous difference for you and for your kids. And that's a bigger concern than you do. So you really should try your very best to get started immediately, as soon as you can, on safe investments that are actually things that are growing. Safe things, not outrageous sub-penny stocks. Never buy sub-penny stock. Don't do that. Don't do that. Oh, did you hear about, this is bringing something to mind. Did you hear about one of these, I think it's Ethereum. Ethereum, one of these, Ethereum, one of these cryptocurrencies. And so apparently, some individuals that are part of famous families decided they wanted to mention this thing because they want to promote it, and they think that people in their family prevent the Securities Exchange Commission from doing anything against them about doing something illegal like this. And then somebody in their family went and said, oh, maybe we should have a national reserve of this cryptocurrency. Maybe the federal government should be putting money into this and buying this cryptocurrency, which then, of course, bolsters the cryptocurrency, makes it trade higher, so that family members can get benefit from this. I will not mention names, but this is interesting.
Mm-hmm.
Don't buy sub-penny stocks. Don't do that sort of trading. Don't do it. If you benefit